Hi, welcome to Genesis Engineers Academy. In this video, I am going to discuss on thrust bearings. So, thrust bearing is nothing but which supports and guide the shaft. So, in which the end of the shaft is in contact with the bearing surface. So, generally, here the prime contact is end of the shaft. So these thrust bearings are primarily used in propeller shafts or wind turbine shafts or water turbine, steam turbine, whatever it is. So this shaft or propeller shaft will be subjected to axial thrust. In that case, this thrust bearing is used. A bearing surface provided at the end of the shaft is known as pivot, and that provided at any place along the length of the shaft with the bearing surface of revolution is known as collar. So if the end of the shaft is having this bearing, then we call it as a pivot bearing and thrust bearing. The thrust bearings are of two types. One is footstep bearing or pivot bearing. The other one is called collar bearing. So due to axial thrust, which is conveyed to the bearings by the rotating shaft, the rubbing takes place between the contacting surfaces. So this produces friction as well as wearing of the bearing. Here, the basic principle we use in deriving the equations to find out the torque to be transmitted. So the rate of wear is proportional to PR, where P is the bearing pressure, R is the radius of the shaft or sometimes collar. Okay, so first assumptions. So we made two assumptions here. Firstly, the intensity of pressure is uniform over the bearing surface. In that case, the pressure is made as constant. So we have the equation PR is equal to constant. So in this equation, if P is made constant, that means uniform pressure over the bearing surface, then we can get the one formula. And if both P and R is equal to constant, then we call it as uniform wear, because rate of wear is directly proportional to PR, bearing pressure. Understand? So this assumption holds only that is newly fitted bearings. So newly fitted bearings means there won't be any wear and tear, and you can make the surface so that the intensity of pressure is uniform. You understand? So that is that means the fit is a very perfect one. That is one assumption. The other assumption is the rate of wear is uniform. So this conception or this assumption is for old, that is PR is equal to constant. In this P is constant. That is the thing we assume. So this assumption of uniform wear gives us better practical results, because new is only for a few days, and after that the wear and tear takes place. So this uniform wear is more practical than the uniform pressure. The flat pivot. So the thrust bearings are footstep bearing or flat pivot. So there is another bearing called pivot, conical pivot. So it is flat pivot. So this is the this one, this is the shaft, and this gap, here we provide some soft materials which will act as a bearing surface, and this groove is for oil, and here the shaft is rotated, and because of the loads acting on propeller shaft like wind turbine shafts, the load, axial load, acts on the shaft. Okay, so let W is the axial thrust or load on the bearing, and R is the external radius of the bearing. So this is R, and the pressure, intensity of the pressure is P, and the coefficient of friction between the contact surfaces wherever. Okay, so mainly we concentrate only on that area. So this is, if you take this as this one, and suppose a small ring for our calculation or derivation purposes, and this thickness is dr, and it is at a radius r. So we measure, that is pressure P into, this is the surface area, that is 2 pi r into that area is. So this is the area of the elemental ring. So the bigger ring radius is capital R. So this is the pressure, this is the area that gives us force, or otherwise W. So W is integral 0 to R P into 2 pi R, that is perimeter, into dr, that is area. If you take that one, so this is the total load, that is 0 to R P into 2 pi R into dr. If you want, you can also derive. So here the variable is R, so it will have this P into 2 pi R square by 2. 2 gets cancelled, so you will have P pi R square, and you have to substitute capital R. So this W will become P into pi R square. That is the thing you can calculate what is the load based on the intensity of pressure. So that total frictional moment M is equal to this one. How did you get this? So this is the W, then mu W is the frictional force, into that is R will get frictional moment. So this is the frictional force, F into R is the moment of force, then it is called, because we are using frictional force, that is why it is called frictional moment. So if you that is integrate, you are going to get that is, for while that is carrying out this integration process, first assumption uniform pressure. So uniform pressure means this made as constant, and you will integrate this part, and you will get W is equal to P, that is intensity of pressure, and pi R square. And if you integrate this one, made this PR as a constant, and you have to introduce C, then you have to carry out. For diploma purposes, the derivation is not necessary. That is why I am skipping off. I will make another video deriving this equation for BTech people. And these are the two formulas to find out the that is thrust load, that is the pressure into area, and this one, and you can also calculate this is the area of this one. Okay, so that is the pressure acting on that one. So the pressure into area, that is pi R square, so where R is the radius of the shaft, and the that is frictional moment is equal to 2/3 mu W R. So 2/3 mu W, it is the force, and it is, that means the force or the moment is from 2/3 of this radius. Okay. Next one is considering rate of wear, that is PR is equal to C, the total load is this. And that to PR has been taken as C, that is constant. Okay. Next, W is equal to 2 pi RC. So from this, you can calculate what is C. Sometimes that C may be used for calculating the moment. So here, this is that one is 2/3 mu W, or considering the uniform pressure, this is half mu W R. So this is for uniform wear and this is for uniform pressure. Okay, so uniform pressure is more moment and uniform wear is half. Okay, so this is about flat pivot or footstep bearing. Next one is collar bearing. So we provide a collar and you can also use this one. What is that? So there is a gap in this. If you apply, you can also provide some metal like this one if the shaft is a soft one. And okay, here also that is a metal, and also here metal or some other even bearings also provided. Okay, so this is about collar bearing. So this is the collar. So this is the one diameter, one radius R1, or otherwise you can say this is R1, this is R2 based on this one. In the previous case, there is no collar, and if the load is more, we'll provide that is multi collars also. That I will discuss now itself. Now let W be the axial load or thrust, external radius of the collar and internal radius of the collar. So external radius is this one. Okay, internal radius is this one. So external radius is R1, internal radius is R2. That is shaft diameter is R2 and collar outer diameter is R1. So in the same way as we have derived, that is for flat bearing, and for uniform pressure you are going to get this one. Okay, if R2 is becomes 0, you will have pi R square as we have derived. Okay, so if you remember this one, you can also apply for flat pivot. This is the equation for collar bearing. If the collar is not there, R1 or R2 may be 0. Okay, so you will have pressure into pi R square. That is for flat. This is for collar. And this is 2/3. You understand? So this is R1 cube minus R2 cube by R1 square minus R2 square. If you R2 is made as 0, if that is collar is not there, so R1 cube by R2 square is R1. Then what you get? This is 2/3. Okay. So for the moment, you have to take that is nothing but torque. This is nothing but torque. So this is about collar. For uniform wear, and this is PRC is equal to 0, and you will have this W by 2 pi R minus R1 minus R2, and M is equal to this one. Even if you made this as 0, that is you will have half mu W R. That is for flat. Okay. If you remember the formulas here for diploma holders, there is no derivation, but I have simply explained in a shortcut that how to derive, that is on integration. Okay. So finally you have this one and this one. For weight or total load or axial thrust, P into pi, that is the area. Okay. If you made this as 0, you will have for flat. Okay. So for flat it is 0, For flat it is 0. Okay. Next one is if you for flat it is 0, you will have C for that is flat bearing. Okay. Next in this case also 0. So you have to remember this equation is enough, and for flat you have to make this R2 as 0. Then you will get the equations for flat, pivot or footstep bearing. So there is a limit to the bearing pressure on a single collar, and it is about 0.4 MPa or otherwise 0.4 Newton per mm square. Where the axial load is more and the pressure on each collar is not to be allowed to exceed beyond the desired limit. So, okay, if one collar has to bear the total load, it may not be possible. In that case, we divide the things and we make so many collars. So, how many collars should be applied, that is added. So, these are the collars, and number of collars is equal to total axial load and the permissible axial load on each collar. And okay, suppose it is 400 newtons, and if it is that is only load allowed on each collar is 40, then you have to use 10 collars. Suppose it is 80, then you have to use 5. Like that you can calculate number of collars. Very important formulas. So in this video we have derived and have to know that is W is equal to pressure into pi into R1 square minus R2 square. Okay, considering that is okay, and like that moment is also 2/3 or all these things. You can also calculate mu W into R1 cube minus R2 cube, and you have to remember. That's all for today. Subscribe if not subscribe, and also press the bell button. Don't forget to press the like button. Share among your friends if you are enjoyed this video, and comment